Welcome, this video is about shadows, similarity and enlargement. We cover measurement as well, from cubic centimetres to cubic metres. We look at ratio theorem, tessellation, reptiles. There is so much on this video. I hope you enjoy it.
So, welcome everybody, glad to see you. Today is going to be about a really important topic in mathematics, similarity and enlargement. Okay, so you see some of the activities we're going to investigate today. So I think you all know me, I'm Tony Bearden. I love working with children in school and with teachers. Recent years it's been mostly with teachers. It's been a great pleasure. I started AIMSEC 20 years ago, and here we are still. And Caroline?
Hello everyone, my name is Caroline Ainsley. I'm the founder of Bubbly Maths, and we want to make maths fun, enjoyable, and my mission in life is that every child on earth will love learning and enjoy mathematics. What better way to do that than to reach teachers with Tony with all these wonderful hands-on activities where you learn by doing rather than by being taught.
Hello everyone, and thank you. I'm happy to join you here today. I am Samuel Okoth Ogalo. I am a teacher from Kenya, and a maths and science teacher who is supporting other teachers to make the best use of technology in teaching and learning and making learn fun and enjoyable.
We are going to imagine ourselves going up this spiral. This is a learning spiral starting in early years before the children arrive at school. And each year or each phase of school, they're likely to meet the same topics again and again and again, reinforcing their knowledge and learning more. And this will be the pattern today. We'll start with the very simplest stuff for young children, and we will build on that and come to much more searching and deep mathematics as we go on later on. So we're going to work on similarity and enlargement, scale factors, tessellation and tiling, and some trigonometry definitions. And these are all the activities we'll be engaging with. You can read them for yourself. You'll see there's quite a lot of them, so maybe we should get started.
Great. So have a look at the photo that is showing up, and I want you to think about one thing. All of us have experienced this at least once in the present or the past. Is your shadow always the same length every time, or does the length of your shadow change from time to time? Now, I want us to think about this and think about cases where we have had an opportunity to look at the length of our shadow. Does it always remain the same length? And if yes, what is the same length? If no, is there times when it is shorter or longer? And why do you think so?
Well, here are some shadows that are cast by solid objects. They're not just flat, they're solid, three-dimensional. But what you see on the wall are shadows that look two-dimensional. So what we want you to imagine is what 3D objects could have made those shadows. Sometimes there's more than one answer there for each shadow. And can you draw different shadows that the objects could cast? Different shadows that could be made by the same objects. So we suggest this is something that you can invite your learners to do, and they can have some fun doing it, but also learn something about the shapes. So what shapes could have cast those shadows?
I'm using my phone. I'm going to be using my phone to produce the the light. That is what is going to be producing these shadows. And these are the items I'm using. I'm going to use a plum, a child's toy, part of a child's toy, another child's toy, although that's adults too. Got an octahedron here, and a pyramid. Of course, these are cubes. The light's about to go out, and we'll see what happens. Well, I'll just have to leave that one open. Right, you can see my phone there. And we're going to see shadows. So Tony, give me instructions. I've already looked at that.
Well, let's start with the cube, shall we, Caroline?
Right.
Now, of course,
I think I'm going to go with this one because I've built the little.
so you see, we know the cube, we can see that the cube is three-dimensional, and you're getting different shadows. Caroline's using her, oh, that looks really quite long and thin. She's using her torch on her phone, and she's showing that just from that one cube, you can get different shadows. You can get a pentagon. Is it a pentagon or is it a hexagon?
I've got to, everything's left is right and right is left. I'm doing my best to. I must be going up, but there we go.
Now, number 2, if you remember it on my slide, was just a square. And you could probably just show us a square, Caroline, could you?
I will do my best to do that. But I think the best way I can demonstrate it is imagine a square directly under it. But let me see if I can make a square. Let's see if I can manage to make a square. That's
you really have got
close.
the light directly behind the cube in order to do that.
Right, yes. The thing is, I can't show you the shadow and do that. What I can do, discovered earlier, got to keep. It's much easier to do this in the classroom on this visualizer.
Well, that's a rectangle.
That's yeah, I've got a good not a bad rectangle there at all, is it, Tony? Now, see if I can move this round.
So how about showing us what you can get with the ball, Caroline?
Right. I'm going to use the plum. And what I like, we can move it further away.
Now she's stretching that image that we're going to look at Shears a bit later. She's actually getting a shared image of the plum by...
It's changing the area though, isn't it, Tony? What I'm doing here,
yes,
the area of the shadow is not the area of the cross section of the sphere, the plum sphere.
It's interesting, isn't it? Now, if you have the light directly above the plum, and then your shadow is a circle.
Okay, yes, we can see it with this because it's a sphere. You can see the circle because it's not, and this is slightly enlarged. I can make it a circle, and I think it's ever so slightly enlarged. That's quite nice.
And of course,
and then if I move the plum away, well, we're going to that's what we can see later. We'll do that later.
Yes, that's nice. And of course, if that was not round or spherical, if it was a cylinder, you could show the same image. So number 1 on the slide I showed you was just a circle, a shadow which was just a circle, and that could have been made by a cylinder as well as a...
Well, this is a cylinder, and look, we've got a circular shadow.
Well, yes.
Around it. I mean, it's not exactly right because the shadow is actually at the top of it, but essentially you can see what is effectively a circle.
You also had an octahedron, didn't you, Caroline?
I've got an octahedron. Now, the beauty with the octahedron is you can also make a square. And let's see if we can do that with the pyramid as well. Here we go. If I move, It's hard to tell which one's supposed to go. There we go. It's a kite at the moment, but if you move it just right, you can also make it, because you can see the cross section.
Well, that's a nice kite.
Show you the octahedron. You can see the cross section. Well, it's hard. This is very bright light. We had to make it bright light. But if you look at the top of an octahedron, it is actually a square. There it is. The cross section is a square. There, you can see it. So you can make a square shadow with an octahedron.
Okay, did you have any more shapes you wanted to show us?
Yes, I've got a tetrahedron. And again, you can make a quadrilateral. I'm doing my best to dangle it without wobbling it. Okay, move it there. There we go. Now, so we can make a triangle, quite easy to do, but we can also make a quadrilateral. And if you shine it in just the right place, you can make a kite. So you can really look at symmetries. It's hard to do, I'm sorry. Go. Skills.
Well, you're obviously having fun, Caroline. Let's move on, though.
Oh, you're spoiling my fun, Tony. Okay.
Going to the teachers here is, this is something, especially with younger children. I mean, we're very near the beginning of this workshop. So
for younger children, because you can really talk about you can go into quite deep depths with the older learners, and they will be engaged just like I was. I didn't want to stop.
And now, if we move on, we've got some pictures here, and we're asking what shadows can these 5 regular polyhedra make? So just as an example, the tetrahedron there it is. Now I've blacked it out. I could make a shadow that looked like that, but it could, as Caroline showed you with the tetrahedron, from different angles you can get different shapes, shadows, and I've drawn the yellow dotted lines which show you the edges of the tetrahedron, but one of them is at the back, so you wouldn't actually see that. You just see how the tetrahedron could make the shadow could be a quadrilateral. So as the light source moves, the shadow changes, and you can experiment with this yourself. Now, one practical use of shadows, and it was for many, many years the main way of telling the time, the sundial. Tell us a bit about the sundial, Sam.
Great. Now, the whole idea about the sundial is making use of the sun as it appears to move through the sky, so that it can align with the different 24-hour lines, and these are used to indicate on the dial the time of the day. Now, if you closely look at the picture that we have here, look at 4 and 9 on the dials and see any difference. Have a closer look at 4 and 9. The way that they're represented using the Roman numbers is has been pointed.
4. That's 4 there.
Yes.
And 4 here is this one. 9 is here.
Yeah. Yes.
And 9 is this one. So what's the difference? Especially in a primary school, this is a really good exercise. You can either go and visit one if you've got a sundial near your school, or even in the school grounds, or you can make your own very simply. All you need is a pole, really, and you can make the markings around at several different times of day to show the time where the shadow points to each of the hours of the day. You could just mark on your your son down. It'd be a very good exercise for a class or a group to do in school. Caroline, would you like to talk about similarity?
I would. You can see, well, one of my favourites, I'm going to call him a person, Pooh Bear, Winnie the Pooh from A.A. Milne. He's wearing a Tigger onesie, so that makes me super happy. But you can see that there's 3 different sizes of him, the same proportions. If you draw a line through the same point on the different sized images, take 3 points in this case. So we've got the base of the image, choosing Pooh's nose, and then one edge of the image. The place where they join is the center of enlargement. If you're watching a movie that's been projected, the center of enlargement again is the source of the projection, which is like my camera light source. And the triangle I had would have been the green bit, the X, Y, Z in the middle. And the shadow would have been X dash, Y dash, and Z dash, with P being the center of enlargement and the source of the light. The important thing is that there is no distortion. The corresponding angles are equal. There is no distortion of the image, just like they are similar images. They are the same, but different sizes.
Now we're going to ask you to do an activity, actually 3 activities here. What we have got is yellow L shapes made of just 3 squares, and red L shapes and blue. So for each one of them, we want you to make an enlargement of that shape by fitting together 4 identical smaller shapes. Now you can either use squared paper and color them in for yourself or outline them, or the easiest way is to cut out the pieces to make the 3 puzzles. Now, if you have got the worksheet, you'll see that there's spread paper on the worksheet, and there is also there are also large pieces. So I think Caroline's going to try to do one of them. So you try to do it. Don't just watch Caroline and copy what she's doing.
They're not going to be able to see what I'm doing. I'm just showing them right now that I've got it all ready. Now you can have them cut out. If you haven't cut them out, then just on a piece of square paper. This is 2 squares. This is 3 squares. The L, 2 and 3. This is 1, 1 and 1. And this one is a 2 by 2 square with 1 sticking out. We've got to make the same shape using 4 of these smaller shapes. So an enlargement, a similar shape.
We give you a few minutes to do that because
I'm not going to show them. I'm going to turn my camera off. They're not going to see what I'm doing, but I am doing it. So please do it. You can draw on a piece of paper as well, drawing it.
While you're doing it, think what you're making is an enlargement of the same shape. So for the yellow one, it's going to be not 3 1 by 1 squares, but 3 2 by 2 squares in the outline that you're going to try and fill. So you're making enlargements of the shapes.
Ooh, I've managed to make the red one, the L shape. So that's it. Yes, it is. It is to scale.
We're pausing now to give you time to do it. You could.
Not sure about this blue one, the one with the. This looks awfully hard, actually.
So could you?
I managed to make a rectangle out of the one with the 2 by 2 square and the one extra. I've made a rectangle. Is that can I use that, Tony? Or do I need the? I'm
No,
just joking. Tony, I'm joking. That was a joke. Sorry, it was a very bad joke. Oh, can we turn them over? Do they have to be the same? They don't have to be the same way around, do they? Do they?
Yes, I think you can. Yes.
If I turn, there's a hint for you. If I turn the one with it says 2 by 2 with one sticking out. If I turn one of them over, I've actually managed it.
On the right, we've got 3 small buildings made with cubes. Now, count the cubes in each building. So can you see that the smallest building is made with 3 cubes, it's an L shape, and it's the 3D version of the first of the 2D puzzles we did, the yellow one. Now the edge lengths of the other 2 buildings are doubled and trebled. So another way of saying that is that the linear scale factors of the enlargements are 2 and 3. So the edge lengths are doubled, that's a linear scale factor of 2, and trebled, that's a linear scale factor of 3. So let's see how that affects the number of cubes that we've got. The middle one has 3 blocks of 8 cubes in them. So that's 3 8s of 24. And the one on the right has 3 blocks, but each of those has 27 small cubes in it, and that makes 81 altogether. 3 times 27 is 81. We said that the linear scale factors, the edge lengths, are doubled and trebled. What about the area and volume scale factors? Now the area scale factors are 2 squared is 4, and 3 squared is 9. So if the linear scale factors are 2 and 3, the area scale factors are 2 squared and 3 squared, 4 and 9. And the volume scale factors are 2 cubed, which is 8, and 3 cubed, which is 27. You know that the volume scale factors are the cubes of the linear scale factors. So what we have there is the little building has 3 cubes. The middle-sized building has 3 blocks of 8 cubes. That's 3 times 8 is 24 in all. And the building on the right has 3 blocks of 27 cubes. That's 81 in all. Now here's the answer, and you can, I think Caroline is showing us that that she has done these 3 puzzles. They're quite simple. Now it's really...
Yes, and my solution is actually slightly different to your one as well. So there's clearly more than one solution. My red and my yellow are the same, but the blue one is different.
But it is still an enlargement. Okay, so Sam, here we've got some more examples of similarity and enlargement.
Yeah, so we're going to have a look at the 3 little men, the 4 little men. They are in line from color blue, green, yellow, and the last color is orange. Now, if we have a closer look, you will realize that the first color who shows in color blue is similar throughout to the last who is in color orange. If you have a closer look, they have every kind of similarity, just except in the size and in the color, which is bringing us to an idea that the first, which is in color blue, is an enlargement. The last, which is in color orange, is an enlargement from the first as it progresses. So the linear scale factor from blue to orange, to green to yellow to orange, is 1 to 1.44 to 2.08 to 3. And it goes on, and it can give us, if we were to continue with different colors, it gives a different size of an enlargement that started from the little man. Similarly, if we look at it as the surface area scale factor, beginning from 1 to 2.08 to 4.28 to 9, as the color progresses from blue to the orange one. And if we also have a look at the volume scale factor of the 4, it still progresses from 1 to a volume of 3 to 27, to 9, then to 27. The linear scale factor, or just scale factor, is just a ratio that is looking at the corresponding lengths. The first, the second, a little bit longer than the other as it goes on. And the surface area scale factor focuses on the surface area, and then the volume scale factor, same, the volume. And now these scale factors are important to understand enlargement, and we like to use them for either in cases of enlargement or reduction, so that we can be able to find an unknown quantity. Like I was saying, if we were to continue, for example, to a scale factor of a given number, we can be able to find an unknown quantity if we are given maybe two similar shapes with different sizes. So long as we can be able to multiply the relevant scale factor.
So you've got the surface area scale factor is the square of the linear. So 9 is 3 squared, and the volume is the cube of the linear scale factor. Now we want you to think about what we have in large part of the world as our standard paper sizes for printing paper, A4, and then the larger pieces of paper where you see posters are in the same proportions. And there's a video here which we're going to show you.
This video is about scaling paper airplanes. You will need 5 sheets of scrap paper, A4 if possible, and a roll of sticky tape, or scotch tape, or sellotape, depending where you are in the world. If you want to make the really big one, you're going to need 64 additional sheets of A4 scrap paper and 2 long rolls of sticky tape, 5 if they're small. Get a sheet of scrap A4 paper and make a paper airplane. And I'm going to shoot mine and see how far it can go. Woo! Hey, that's not bad. 2 pieces of paper and stick them together. Remember that ratio, the paper must look the same, so we don't stick them together like this, because this bit's way too long there and this bit's way too short. We stick them together like this so that the ratio is the same. And we're going to stick those 2 together, so we've got those 2 stuck together like so, and then we're going to make it even bigger. We're going to stick 2 of those together to make it even bigger, and I've got that here. And when I do workshops in schools, you don't stop there. You keep going and going and going and going and going until you've got a really, really huge bump. But right now, you can do that later. You can make as big a piece of paper as you can. But the ratio must stay the same, so it's got to be a scale model airplane. Can you imagine how big do you think you can make that piece of paper, and how big do you think you can make that airplane? Who's up for the challenge? Put your hands up if you're up for the challenge to make a super duper uber giant airplane. In the meantime, I'm going to test this one. Let's see how it flies. Woo! Well, that wasn't very good, but I didn't finish it all and I didn't fold it properly on a table. Okay, next one is, we're somewhere here. Whee! Oh. You could, if you like, do something later. You could halve the size of the paper that you started with, or halve it again, and even halve it again. So you're making a scaled down version of your airplane. Make different size airplanes, see how they compare, and see how they fly. Look at the engineering part. Which one flies best?
So we got a massive piece of paper, which is amazing. Okay, you grab that.
Yep. This is
3,
2,
2,
1.
1.
So you see, if you put two pieces of A4 together, you make an A3, and the ratio from the shorter edge to the longer edge is 1 to root 2. Shorter edge is 1, and for A4, the ratio shorter to longer is 1 to root 2. So the linear scale factor, what is that? What's the linear scale factor and what's the area scale factor? If it's 1 to root 2 for the linear scale factor, then you square that to get the area scale factor. So it's the area scale factor is 1 to root 2 squared. So it's 1 to 2. And you can see that here, can't you? So going from A4 to A3 is going from 1 to 2. Double A4 gives you A3, and so on. And all the paper sizes are given in this table here. And they're all based on the A0, which is a big poster size, being a square meter in area. Think of some questions you could ask to start exploring one of these images you see here. That's why it's called talking points. To see one of those images, what sort of mathematics could you get out of it? How would you explore that to get some mathematics out of it?
We are now going to put on our teacher hats. And now I would like you to think about this. What kind of questions, or what questions can you ask, or might you ask as a teacher about this slide, the slide that is showing on the screen? What questions, or what key questions do you think you can ask while using this as a teaching resource, that what is on the screen? And why might you ask such questions? Or in other words, in what cases, I would like you to think about what cases you would use this particular resource that is on the screen. And what key questions do you have about, do you have when you are using this resource, and why?
So the question is now specifically about this diagram, and ask your learners, what do you see in this diagram? Indeed, what do you see in this diagram? It's made up of 3 sets of parallel lines, and this is something that is useful for your learners to do, to actually create these parallel lines accurately using tracing paper or wax paper from the kitchen is a good way to do it. So you've then got, you don't have the little squares on it. So do that on squared paper or use measuring tools. And then once you've drawn it, you've got you've got multiple small diagrams. We're just going to look at the one that's grayed out in the center, marked 1, 2, and 3. Just look at that one triangle. We're going to call that triangle T. So we want to get your learners to label each of the angles, 1, 2, and 3, and then look for all of the angles at the same as 1, angle 1. Remembering this is all made up of parallel lines, 3 sets of parallel lines. So label all the ones that are labeled 1, then label all the ones labeled 2, label all the ones that are labeled 3, and then just go back to the ones labeled 1. Why are they all equal? This is really powerful in working out a few of the rules of parallel lines as well as the rules of triangles. So once we've had a discussion about that, then look at the larger triangle. It's a similar triangle, but it's larger. So what about, first of all, how many copies of the original triangle T are within it? And then there are so many other questions after that. Why is it similar? What are the angles of the larger red triangle? On the worksheet, you've got a small sample of this so that you don't actually have to draw it, but you want a decent size one to do it. So the next big question is, can you use this diagram to show that the angles of a triangle add up to 180? You've now got all of the angles labeled, so you will find that on every junction between every intersection, you will actually have multiples of 1, 2, and 3 on one side and 1, 2, and 3 on the other. And that's a really lovely way to see that the angles of a triangle add up to 180, and also that a straight line made up of 180 degrees. There's a lot of very rich geometry in here. Tony.
Well, here you have the same tessellation. Did you notice that word tessellation? When a shape, copies of the same shape, identical copies of the same shape, fit together to cover the plane, that's called a tessellation. Now, what Caroline was talking about is this triangle, which is ABC, okay, enlarged to the triangle AFE, and 4 copies of the small triangle fit into the triangle AFE. So we've got a linear scale factor of 2 and an area scale factor of 4 there. And you've got, in here, you've got the angle 1, most of the angles are equal to angle 1 marked. And if you look at this point, you see what Caroline was talking about. This is equal to angle 1. This angle here is equal to angle 2. And on the right-hand side, equal to angle 3. And you see they fit together on this straight line, so they add up to 180 degrees. So angles 1, 2, and 3 add up to 180 degrees, the angles of a triangle, and that triangle. And you can do the same tessellation with any triangle and show the same thing. So here are some of the names that we use. You've got opposite angles. So where you see 1 and 1 here, 1 and 1 here, they're just opposite angles with two intersecting lines. Adjacent angles are like here, you've got adjacent angles on a straight line. 2 is adjacent to 1 and 3 there, and alternate angles, adjacent angles, that one and that one are adjacent. Co-interior angles, this one is co-interior to angle X, and alternate angles, this one is, if that is X, then this one is alternate to angle X. So this is a nice way to sum up, to explore tessellation of triangles, and to sum up what you need to know, what the learners need to know about parallel lines and a transversal. Here you've got the arrows on parallel lines, and this line going across is the transversal there.
This particular activity of tessellation and tilings brings me to remember an activity we once did in a maths club when we were finding out polygons, any regular polygons that can be dissected into smaller, equally sized copies of themselves. And so a shape, any kind of shape that can be dissected into a smaller copy of the same shape in geometry is called a reptile or a tile. And this particular term was coined by Solomon, and later on popularized by Martin Gardner in his mathematical games. So imagine any kind of a shape, or any kind of just any kind of a shape that you can be able to dissect into smaller copies of the same shape. And imagine having this maybe in your pavement, and maybe having this repeating shape in your floor. Imagine how it will look like.
And the tessellation there is all based on the L shape with 3 squares, which we had earlier on, the yellow one. And here you see how you could go on tiling the whole floor with the same pattern, and showing enlargements of that basic L shape. It's a reptile. Caroline.
So we're back to me and my colouring in and bits of paper. So what we've got here is a reptile that we call this. That's called the Sphynx for obvious reasons. It looks like the Sphynx. I think it's very well named. It's made up of 6 triangles, and the challenge is you can do it 2 ways. You can either cut out one Sphynx that's made up of 6 triangles, or look at the larger shape and draw the outline of those 6 of the 4. Sorry, it's a reptile made from 4 copies, and see if you can draw the outline of 4 of those Sphinxes. So I'm actually going to have a go at that. So I've got the worksheet here. If you don't have the worksheet, it's not that problematic to just draw out those triangles, a few parallel lines next to each other, but have a go, please. This is definitely a have a go workshop, and I'm going to have a go while I'm doing that. But in the meantime, the questions, I'm going to colour the outline. And we're looking for, while you're thinking about it, what are the scale factors of this enlargement? So we're looking at length and area. And then once you've worked out how to enlarge one Sphynx to one using 4 Sphynxes, repeat the process, and you could do this with your learners to make an even larger Sphynx with 16 copies of the original small one. Think about the scale factors and have a go at the worksheet. I'm having a go now. Not quite sure how well I'm doing. I think I should have done this with a pencil. Oh, found one, found 2, maybe. Tony, is there something you'd like to say while we're thinking about, or should we just do this?
Again, you can, as Caroline has said, you can think of putting 4 of those Sphynx shapes together to make the bigger one, or you can think of, as Sam described it, taking the bigger Sphynx and dividing it up into 4 smaller Sphinxes. And of course, if you can do that, you can do it again and again, making it fitting in smaller and smaller ones. We'll see some examples of that sort of thing in a minute. And here is the same question. So shall we look at the answer?
Oh, I was nearly there. I was getting there. I just had to reverse the red and the blue, and I was there. I was just getting to that point. To give your learners a chance to do that, it's a really powerful activity. And then now we've got the scale questions.
Sam, you talked about this earlier. So what you have here is, again, it's like the we saw earlier with the imagined it as a floor tiling, but here it is again. So you see the second one, the middle one at the top, you've got 4 copies of the L shape. In the one on its right, you've got 16 copies of the L shape, making the bigger one. So as you see, is what Sam said earlier, you can go on doing this, fitting each stage, fitting 4 copies of the L shape into each L shape, and it packs it closer and closer. So this is what we call a fractal. It's based on a shape made up of 3 squares, and each time you draw the next one on the worksheet, and you get this packing. And you in practical terms, it would be difficult to continue it any further than this 6th one, you see, multicolored one. But in mathematics, you can imagine going on forever doing the same thing. You're sort of zooming in on it. Here's
just watch this one. Just have a look. You can see the 3 colors: yellow, red, and blue. And learners know these are the primary colors. And look what happens when it gets it's doing. We're repeating the reptiles. We're looking at a reptile fractal. As it gets into more and more detail, it turns, as you've seen several times now, it turns white. The red, yellow, and blue, when they're at a small enough scale, it's like the presence of all colors, it turns white. This is very cross-curricular. You've got the science and the maths working together, so you can see how the maths is critical in the science, and you've got the red, yellow, and blue by mixing those 3 primary colors in light. 3 primary colors. The presence of 3 primary colors gives you white light with light, and that's what we're seeing here. And this was you can see the rainbow there, the primary color mixed rainbow wheel by Johannes Itten in 1961. So a lot of work has been done this, and there's also there's a link there to give you more information, which when you get the PDF, you can click on and read more about it.
Yes, and if you want to use it yourself, you can go to Wikipedia and copy it.
I beg your pardon, Wikimedia.
Yes. Now, here's a selection of reptiles. All of the images that you see there, different ones, but they're all reptiles. And the number, like a rep 2, has got 2 copies in it. There's one. There's a rep 2. It's got 2 copies of the triangle inside the triangle that you see. Now, there are some rep 9s, whether or not there's one. If you count them, you will see that there are 9 copies of the smaller trapezium in the bigger that fit into the bigger one. Here's another one that's a rep 9, and there's indeed another one. And you could ask the learners to classify them, and it just requires them to see how the tessellation is being put together and to count how many small ones go into the larger copy. So there's some reptiles, and this is an intriguing one.
And I love this one. So you can see they're not, well, we saw that in the previous one, but we're having a close look at one that's not, where they're touching, the reptiles are touching each other, but it's made up of effectively 3 triangles, 2 making a rhombus and a separate triangle making that the fishtail. And you can just see that the possibilities are endless on how you can make reptiles, and it's mesmerizing to look at. And you can fit the same shape inside of each fish inside of itself again and again, so it gets infinitely small, producing a fractal. And using isometric paper, you can make this pattern, many others for yourselves. You can challenge your learners to make a rep 4 or a rep 2 or a whichever rep it works out to be. Tony.
This is a rocket, or sort of, representation of a rocket. And the reason for having that little equilateral triangle there is, if you look into it, you'll see that the rocket shape, there's 3 copies of the rocket shape, one in red, one in green, and one in blue, are fitted into the triangle. Now, if you go over to the right, there's the bigger rocket. Okay, so the bigger rocket is 1, 2, 3, 4, 5, 6. The scale factor of the enlargement is 6. So we go from so the linear scale factor is 6, and the area scale factor therefore will be 36. So if we can fit 3 little rockets into each triangle, each red triangle here below can also have 3 little rockets in it, and so we can fill this bigger rocket with lots of smaller rockets. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 triangles here, each with 3 small rockets inside. So there are 36 small rockets can fill this larger rocket. So the area scale factor is 36, and the linear scale factor is 6. 1 to 6, 1 to 36. I think that's quite a lot. That's fun. I like that one.
I love it. Sam's still dark, Tony, so could you talk about this one as well?
Yes, so just take an ordinary pack of cards and very carefully just push them gently so that they shear. So what you've got there is, if it's done perfectly, the edge here will be just plain. You won't be able to see the edges of the cards. It's very difficult to do it, so it's absolutely flat on this edge here. But that's showing a shear. Everything's pushed over, and here's some shears. And
And
you
this,
see,
what I find really useful about this is you can see if the height is the same, so you start with the original triangle, whatever triangle shape that is, if the base is this, as long as the base is the same length, it doesn't matter, and the height is the same, you can move it across, and that is a shear. And the area doesn't change. This, to me, is a huge insight on the area of a triangle. Half the base times the height. You can move the top of the triangle as far as it will go, as long as the height remains the same, and the area will remain the same if you don't change the size of the base. On the far right, you've got the three shapes where the base, either the height is different or the base length is different, in which case they're not shears. And then we've got the same with the circles. Again, as long as the height is the same from bottom to top, they're not all circles, obviously, but a sheared circle, the area will be the same, whereas the one on the far right, that ellipse on the far right, squished down shape is not a shear because it doesn't have the same.
so let's look at this. This is very similar to the picture that we had with Pooh Bear, an enlargement of Pooh Bear. And it's what you really need to understand why we have the definitions of sine and cosine in trigonometry and how it all works. Because you don't, your calculator gives you the sine of any angle that you key in, ask it for the sine, it will give you the sine. But what it's giving you is the sine of all, that's going to be useful for all triangles which have the angle, same equal to angle A. And as you go round this circle, you can get angles bigger than 90 degrees, and the x coordinate is going to be the cosine and the y coordinate is going to be the sine. And you know, if you teach upper secondary, if you teach for metric, you know that the general angle is given by this diagram of the unit circle, and the point moving round has the x coordinate as the cosine and the y coordinate as the sine. Now, if you come back to this triangle, which is a sort of pinky color, you see that the sine and the cosine are the actual lengths of the edges that are right angles to each other in the triangle with the angle A in it and a unit hypotenuse. So if the hypotenuse is 1 and the angle here is A, then the opposite edge length is sine of A, and the adjacent edge length is cosine of A. That is exactly like the triangle you see here in this diagram with the unit circle. But if you change the triangle, making it similar but bigger or smaller, still with the angle A in it, then everything is changed in the same proportion. The lengths are changed in the same proportion. So here you've got P, which is less than 1. I mean, you can see that green triangle smaller. Here you've got Q, which is greater than 1, and R, which is the largest of all. But in each case, you have got these ratios are going to be the same. And that's why you have to divide the opposite by the hypotenuse to give you the sine of this angle. If the hypotenuse is 1 unit, then this edge length is the sine, and that's what's is stored in your calculator. So understanding this idea of similarity and that the values actually are the same for all set of infinitely many similar triangles makes it all make sense. And here's again is another useful link that you might want to use. Now,
Can you leave that there just for a moment, Tony? So I want to say something which you haven't actually said about the previous slide, and that is if your learners just learn to memorize SOHCAHTOA, then this isn't based on understanding, it's based on learning it, and oh yes, if it's this, I need to, you know, this over this, and if it's that, it's that over that. Understanding this, the only thing we have to remember is that the sine A is opposite A and cos A is adjacent to angle A, and everything else is the scale factor of it. And if they can visualize this, they don't have to learn SOHCAHTOA, and they will understand what they're doing. Thank you.
Now, what Caroline is going to show us in a minute is just a little bit of folding here. And so for any triangle, and it's not a special triangle, we don't need to measure the angles, any triangle, you fold the baseline B back onto itself, BC back onto itself, so that the fold line goes through A and R, and it actually makes two right angles at R. So you make a fold by placing A anywhere on AR. So P and Q are not the midpoints, but anywhere on AR. And you mark the fold line PQ. And with P and Q on the edges AB and AC. And then we're going to discuss this in a minute. What do we notice about the lines AR and PQ? So Caroline's just going to demonstrate that.
Okay, so if you stop sharing, Tony, and give me the instructions so everyone can follow them.
Okay, so she's got Caroline's got a triangle. And would you like to mark angles A, B, and C?
Yes. Oh, right, which is, wait, have I got it here? A, B.
That's C.
Oh, okay, I've done mine a different way to yours. A, B, and C. Okay, perfect.
And now you fold the baseline BC back onto itself. So the fold goes through A. And that makes the fold perpendicular to the baseline. Now unfold it and flatten it out. Okay. And that fold line is perpendicular to the baseline. And now you place A anywhere on AR.
Now, I did tell you I was going to do this. I'm going to exaggerate it so that, well, I'm going to do it. I'm making it very, very clear here that I'm not going down to the base and I'm not halving. In other words, I'm not halving the height of this triangle.
And then you can, that line is PQ, so you can put P at one end and Q at the
Draw
other.
this line. And that's which is P, which is Q. P is between A and B. And that is Q. Okay.
Now, and you can mark R at the base there, on the base.
On the base.
And now the question is, what do you notice about AR and PQ?
So AR and PQ. Oh, I'm going to draw the line AR as well as having it marked.
That was your fold line.
The fold line, yeah. So I know what I notice about the relationship between AR and PQ.
So what Caroline has constructed there is AR and PQ are at right angles to each other. And PQ, what do you notice about PQ and BC?
PQ, so these are at right angles. That's 180 between, well, if those are at right angles, that's at a right angle. So I know what conclusion I got between the relationship between PQ and BC.
And you've got a similar triangles there because you've got APQ is
Ooh, so
enlarged
this
to
could,
ABC.
so APQ is yes, APQ is a similar triangle to ABC, and ABC is an enlargement of APQ. I see that very clearly, Tony.
So PQ and BC are parallel by construction, both perpendicular to AR.
So these are parallel to each other, and they're both perpendicular to A, because they're both perpendicular to AR. We're not
And
breaking any rules here, are we?
And notice that angle APQ is equal to angle ABC, and they're corresponding angles. So those two triangles are similar. A triangle ABC and APQ are similar.
So this follows on from what you did with the parallel lines, where you identified all the relationships between angles on the parallel lines. So we know that to be true based on the parallel line rule.
And what else do you notice about APQ and ABC? Well, we'd said it earlier that ABC is an enlargement of APQ. And so we've shown that PQ and BC, so just summing everything up, we've shown that PQ and BC are parallel. APQ and ABC are similar triangles. So it follows that the three ratios, AP to AB, AQ to AC, and PQ to BC are equal. Each ratio is the scale factor of the enlargement. Now, we've gone through that. It's a proof of the ratio theorem. And there are other proofs around which are much more complicated, involve all sorts of arguments about area. This is the simplest and the best proof of the ratio theorem. Let's just summarize that. By construction, AR and PQ are perpendicular. By construction, PQ and BC are parallel, and they're both perpendicular to AR. So ABC is, triangle ABC is an enlargement of APQ. And so we've shown that PQ and BC are parallel, and APQ and ABC are similar. So it follows that these three ratios, AP to AB, AQ to AC, and PQ to BC are equal. And because each ratio is a scale factor of the enlargement, and that is the ratio theorem. Caroline, would you like to show us this second video?
This video is about scale and the cubic metre. This is 1 metre. It's in one dimension and it can only go left and right. This is 1 square metre. It's in 2 dimensions and it can only stay on the plane that it's in. This is 1 cubic metre. This is in 3 dimensions and it can go forwards and backwards, up and down, and right and left. It's so big, I can fit in it. How many people do you think we can fit inside a 1 cubic metre? And each face shows square centimetres. If I put my pinky on one, you can see that it's the same width as my pinky, which is about 1 centimetre. I want you to imagine how many cubic centimetres fit inside my box that is 10 centimetres long, 10 centimetres wide and 10 centimetres deep. How many do you think are going to fit inside? Have a look. How many do you think it's going to be? Every guess is a good guess because what it means is that you're thinking about it. You've got 10 going up, 10 going across, that's just on one face. So if you had 10 rows of 10, how many have you got on the bottom layer? So how many cubic centimetres fit inside? Now, I've got a bigger question. It's a much bigger question. How many cubic centimetres can we fit inside? 1 cubic metre. Have a guess. Here is 1 metre. How many of these are there inside the metre cube? They're both 10 centimetres by 10 centimetres by 10 centimetres. There's my centimetre cube. Here's my metre stick. How many centimetres are there in a metre? How many millimetre cubes fit inside a metre cube? Is it possible to pack smaller, similar shapes inside other platonic solids without spaces between them? If so, how many shapes with edge length 1 centimetre would fit inside the models shown in this picture?
It's a very good little video to show the class and then to ask them the question. So how many 1 centimetre cubes would fit in the cube that Caroline is showing? It's a bit squashed, but it's a 10 by 10 by 10 centimetres, and it's sort of making sense of it when you see in the reality of the little tiny cube and the bigger cube. So we've really now reached the point of looking back at the different things that we have done. So I think what would I like to look at? There's so much here that was quite taxing if we actually worked on it on the worksheet. Which one do you like of all these, Caroline, or do you want to say anything about?
Yes, the reptiles were a new thing to me. You introduced those to me. But I think the thing that I find, I love the scale, and I obviously love the scaling of the cubic meter and the airplanes. But I think the thing that I found most useful, apart from, I don't know, it's all useful as usual. I love that the right angle triangles, the similarity, and starting with the unit right angle triangle. So you don't have to learn Sophocles, you just have to understand what you're doing. But the thing that really, really, really gets me, I love the parallel lines. I love the understanding that you get of a triangle and the relationship between those parallel lines and the connection that it has with the triangle, and just having a deeper understanding of geometry through it, just by drawing a bunch of parallel lines and thinking about it and analysing what you're looking at. I think that is actually my favourite thing.
I like these reptiles, and because you can go on putting smaller and smaller copies inside each one, and you can build it up, making whatever size you've got, making more of those to make a bigger enlargement of that. These are actually the mathematical shape, which is a fractal. A fractal is a shape that you can reproduce inside itself. It's got multiple copies, in fact, infinitely many copies of itself inside itself. And we've called them reptiles here, but These are examples of fractals. Not all fractals are like this, but these are examples. These are all fractals.
I would like to talk about one thing that I've really loved throughout the session. Just as Tony mentioned, I really love the tiles, the reptiles, and specifically how they can be able to evolve into a fractal, and so much that we can even relate to nature. And no, patterns like this can be very fun to just look at. Imagine an art like that on the wall that you can stare at for seconds and minutes and hours pass by, and it continuously causes you to think. That is what I like. I really liked.
Wojtek, do you want to say something?
Yes, welcome everyone. I actually have to say, Caroline, your film with experiencing of the cubic meter, brilliant thing, because a lot of students don't have understanding of the scale factor, and that the movement in one dimension to the second dimension is actually multiplying those numbers, and showing that by those balloons or any other visual means is very useful. But modeling balloons are very useful for this.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.